Okay, good morning, ladies and gentlemen. Thank you for coming to join my talk. My name is Takumi Haruna from Kansai University as a chairperson introduced me. Today, I'd like to talk about the susceptibility of environmental assisted cracking of magnesium alloy using affected by the pH and the aluminum content. As you know well, the magnesium alloy is one promising material. It's very hard to enter. Yeah. So magnesium alloy is one of the promising material of during among the structure of metal to the next generation because of the smallest density among the construction material and easy controls stress by many approach. So magnesium alloy is widely employed for many applications such as automobile, home appliance, and device frames. And as you know, well, also magnesium alloys have some weak points, such as workability, corrosion, and also stress corrosion cracking, environment assisted cracking. And so we should overcome this weak point to contribute to our life and widely safety. And there are so many research on the environmental assisted cracking of magnesium alloy for various P points, such as metal content or microstructure and pre-immersion, chloride concentration. This is the solution parameter, and oxidant potential. This is the electrochemical point of view, and so on. But as you know, the mechanism, whether the ESC mechanism is controlled by active path corrosion, oriented, or hydrogen oriented phenomenon. So I start to research this area. This is the first research of the environmental assisted cracking of the AZ31. AZ31 magnesium alloy in the sodium chloride solution, and by using a constant load test. Here is a change in the strain, corrosion potential, and pH with the testing time. You can see the strain almost linearly increased with increased time and fracture about 90 kiloseconds. pH of the solution start 66.3 and rapidly go to the 9, and then slightly increase to 7 and finally 10. So we realize that it is difficult to determine the pH effect affects the fracture, which pH is the dominant for affecting the fracture. So it is necessary to use the buffer solution. This solution is the pH maintained solution. So I try to investigate the EAC behavior of the AZ31 magnesium alloy in carbonate buffer solution without chloride. And here is the change in the pH solution effect of the pH on the fracture time. I recognize solution pH is constant during the test, and severe ESC susceptibility is obtained at a pH from 9 to 10 here. So present research was intensive conducted in order to understand the EAC behavior of AZ61 and 91 also in the buffer solution as a function of pH and aluminum content also. Here, I'd like to show you the experimental procedure. Material was AZ61, 91 alloy C. And this is cut into this tensile specimen shape. And the surface was polished, mechanically polished with a dry emery paper. Then applied to the EAC test. Solution is a carbonate buffer solution of pH from 8.3 to 11.2. The solution was used at almost room temperature and air open condition. I conducted the EAC test using a constant load type test with reaction vessel or like that. Reaction vessel has reference electrode, pH meter, and solutions. And dead weight corresponding to the proof stress, about proof stress, was applied to start the EAC test. And during the EAC test, elongation and corrosion potential and solution was monitored simultaneously. Here is a result of the EAC test of the AEZ61 in the solution of carbonate solution of pH 8.3. And here is a typical transient of the strain and potential depending on the test time. As you know well, strain, transient, transition was first, second, and third creep aspect. And corrosion potential initially goes up to this value and gradually up to minus 1.5 volt. On the other hand, pH we didn't put in this figure, but pH is almost same value as initial value. So pH was kept. And we see the hydrogen evolution. Hydrogen evolution was severely occurred in the initial stage and gradually mild. So this trend were similar, very similar to the trend under the other condition. So here I show you the effect of the solution pH and solution pH depending on the fracture time. Here, as you can see, the fracture was obtained in the solution of pH 8.3 to 10.5. And when you increase the pH, fracture time gradually and steeply increase. At pH 11.2 here, this solution called no fracture until 400 milliseconds. This is enough with the EAC. So this is again show you the transition of the strain and the strain potential change with the time. If you conducted this test in the air. Only the first and the second creep aspect was seen. So we can define we can determine the clock initiation time as a time when the third creep starts. And clock initiation potential here is determined as the potential at this time. This is effect of the pH, solution pH on the clock initiation potential. When you increase the solution pH, clock initiation time gradually and steeply goes up. As I told you, this is fracture time depend on the pH. This fracture time also gradually up and steeply up with the pH increase. So this finding suggests that solution of the higher pH provides a more protective film, so causing the high potential here and suppress the EAC initiation. Film oriented suppression of the cracking. So this figure shows fracture time depending on the pH as a function of the aluminum content. This is 91, 61, 31 specimens data. Applied stress is a little bit different. This is my mistake, but when you apply the little bit change stress, fracture time is independent of the applied stress, and also independent of the material kind. This is aluminum content in this case, and strongly depending on the solution pH. Here is crack initiation potential depending on the pH. Crack initiation potential strongly depending on the pH here, and also aluminum content. When you increase the aluminum content, crack initiation potential goes up. But this change is not corresponding to this fracture time. This all of this crack initiation potential summarized on the potential pH diagram of this figure. pH and the potential. Red line indicate the equilibrium reaction of the proton hydrogen molecular reaction. Okay. So in this case, crack initiation potential, as I told you, crack initiation potential, lower crack initiation potential at a lower pH like this means unstable film. Lower means unstable. Higher means stable film formation. So this causes the, in this case here, cause easy EAC initiation because of a weak film stability. And also this potential shows larger overvoltage from here. this indicates the hydrogen absorption in the magnesium alloy too easy to fracture. This is a hydrogen embrittlement aspect. Since the change in the characterization potential with the aluminum content is relatively small in this figure, therefore, we may detect the no effect of the fracture time depending on the aluminum content. Okay. So finally, I'd like to conclude my research. The buffer solution maintained initial pH during the ESC test. Fracture time increased with increasing pH, but was independent of aluminum content. Crack initiation potential increased with increasing the pH and also aluminum content. And it is considered that lower crack initiation potential indicated more unstable film formation and large overvoltage of hydrogen molecule generation, causing a high susceptibility of ESC of the alloy. Unfortunately, my research doesn't separate this phenomena is APC corrosion-like phenomena or hydrogen-like phenomena. Thanks for your attention.